There are a few ways to solve systems of equations. We're looking for a solution that works in each of the equations in the system. The first way we're going to look at to solve a system is by graphing. So we have this system, and we look at this system, and we say, okay, these are two linear functions. I can pretty easily graph these from slope-intercept. So let's graph them and see what happens, see where they intersect. We will start with that first one, y equals 2x minus 1. Y equals 2x minus 1, well, let's see, the y-intercept is negative 1, so we'll start here at negative 1. Slope is 2. Up 2 over 1, up 2 over 1. I could also go down to back 1 if I would like. That has enough here for me to make a little graph of this line as accurately as I can, because my graphing needs to be pretty accurate if I'm going to be looking for the intersection of two lines. There's my first one. Y equals 2x minus 1. Let's graph the second one. Y equals negative 1/2 x plus 4. Well, let's see. Y-intercept of 4. I'll do this one in another color so we can see the difference. Y-intercept of 4, negative 1/2, down 1 over 2. Oh, look at that. Down 1 over 2. We've already got something. Or up 1, back 2. You can see as I was finding that slope, down 1 over 2, I came in contact with the first line I already graphed. That's a good sign. Here we go. Now, the intersection of these lines is that point. So that point, since it's on both lines, must be a solution to both of the equations that gave me those lines. The ordered pair is 2, 3. Every time I solve a system by graphing, I'm going to check the solution in both equations, because graphing can be a little finicky if you're not really accurate with your lines. So we're going to use each of these equations. Y equals 2x minus 1, that's the first one. We'll use the ordered pair 2, 3 and see what happens. 3 equals 2 times 2 minus 1. 3 equals 4 minus 1. 3 equals 3. Voila, that one works. Now we will try it in the second equation. Second equation is y equals negative 1/2 x plus 4. The y value we claim is 3. 3 equals negative 1/2 times 2 plus 4. 3 equals negative 1 plus 4. 3 equals 3. Beautiful. So we graphed these two equations, y equals 2x minus 1 and y equals negative 1/2 x plus 4. We saw the intersection of those two lines is the point with the ordered pair 2, 3. We checked that ordered pair, and it works in both of the equations, proving that it is in fact a solution. Let's try our second set of equations, see if we can solve them by graphing too. These equations are in standard form, so I could take the time to convert them to slope-intercept, but I think it's easier to graph these equations in standard form just by using the x and y intercepts. 2x minus y equals 4. The x-intercept, well, if y is 0, 2x equals 4, that means x must be 2. So for that first equation, the x-intercept is 2. Well, the y-intercept is found by making x equal 0. So that would give me negative y equals 4. If negative y is 4, then y must be negative 4. So these are the x and y intercepts for that first equation. And a very careful graph here. I'd like to be as accurate as I can. Okay, the second equation, x plus y equals 5. X plus y equals 5, pretty easy to find the x and y intercepts. If x is 0, y is 5. If y is 0, x is 5. So we have 5 on the y-axis, 5 on the x-axis. And connect those dots to make the line. And we are now looking for the ordered pair where those lines intersect. And it looks like I got a pretty clear intersection here at 3, 2. And just like we did with the first system of equations, we're going to check this ordered pair to make sure it works on both of these equations. The first equation, 2x minus y equals 4. X is 2, y is 3. So, I'm sorry, x is 3, y is 2. That makes more sense. 2 times 3 minus 2 equals 4. 6 minus 2 equals 4. 4 does, in fact, equal 4. We try it in the other equation. X plus y equals 5. 3 plus 2 equals 5. Yes, 5 does equal 5. So our first method for solving systems of equations is by graphing. So we graph each line, look for the intersection, find that ordered pair, check that ordered pair in both equations just to make sure we graphed it accurately and got an accurate solution.